Bismillahirrahmanirrahim. So we covered the streaming of stored multimedia content. So we talked about the real-time streaming protocol, which is the application layer protocol, which is used to set up and control the multimedia session during the streaming of stored multimedia content. So today we'll switch to another topic where we will cover the interactive application, interactive multimedia applications, where we have internet phone, or what we commonly call IP telephony, in which case we have live conversations between two parties, or possibly more than two parties, like one-to-many in a conference session. So this type of applications, we want to study the differentiation or the different characteristics that makes these applications kind of special. So here we're going to take a look at PC to PC internet phone example. So we're going to cover the scenario where we want to have like a Skype chat or any phone-to-phone conversation. So in that case, we need to stream the audio between two parties. So the special case about this is that it's a live conversation. So it's not a streaming of a stored multimedia content. So this is one difference. The other difference is that it's symmetric and bidirectional, but it's not consistent, which means that both sides, they talk to each other, okay? And both sides have intermittent silence periods, okay, which are not predictable. So you have a chunk of audio data going from any direction to the other, okay? And then another undeterministic or unpredictable silence period, okay, from one side to another. Okay, so this type of applications is highly interactive. It's highly interactive in nature, which means that the delay is critical. Okay, so jitter is a very critical component in this type of applications. So we need to motivate this scenario by an example and try to study the special characteristics about this. So as an example, we have an audio conversation between two parties, and audio conversation, if it's uncompressed audio, usually it uses a rate of around 64 kilobits per second. Why is this? This is coming from the fact that usually our voice, from a physical point of view, our voice from the fundamental point of view, is a signal with the typical bandwidth of how much? Does anyone know? 4 kilohertz. Okay, so our voice naturally has a bandwidth of around 4 kilohertz, which means that above 4 kilohertz, it's ultrasound. For us, we cannot actually hear it. So the normal voice is around 4 kilohertz. So using the Nyquist theory, you need to sample the voice signal using a sampling rate of how much? Yeah? At least double, which is 8. So 8 samples per second. Okay? So if we assume that each sample is encoded into 1 byte, this means that we have 8 kilobytes per second. So 8 kilobytes is 64 kilobits per second, right? Because each byte is 8 bits. So if we assume that one sample is encoded into 1 byte, this means that we have around 64. So this number is very common. And this number assumes that we have uncompressed audio. Okay, so this is for uncompressed audio. So this accounts for about, if we assume that we have each 20 milliseconds, we send, one chunk of data. Okay, so in that case, each chunk is about 160 bytes. So if you want to also know where this came from, so we have in 1 second we have 8 kilobits per second, right? So for 20 milliseconds, we have how much data that we can send every 20 milliseconds. It's actually this multiplied by this. Okay, so it's 20 multiplied by 8 multiplied by 10 to the power 3, which in total is about 160 bytes. So every 20 milliseconds, we have 160 bytes of audio packets. Okay, of course, we have to add to this the protocol overhead in terms of UDP header, in terms of possibly RTP header, and if there is any like time stamping and sequencing and so on and so forth. So we have to add this to the 160 bytes. But naturally, that's what we need for uncompressed audio. So the network loss. So we have to define, because just pay attention to the fact that this is a network loss, because we will talk about another type of loss after this, which we did not account for before in our studies. So now we talk about network loss, which is a loss due to congestion in the network. Okay, we have another type of loss, what we call delay loss, and what that means is that a packet, it was not lost due to network congestion. It actually arrived to the receiver, but it has arrived to the receiver too late. So the receiver started to play out, and when it came to the turn of this packet being played by the audio player, I went to the buffer and I found no packets in the buffer. So to me, this packet is as if it's lost, right? Because it arrived, but it's useless. To me, it's useless. So this type of loss, we call it a delay loss. Okay? So it's also caused by the network delay, right? But it was not lost due to network congestion. Okay? So the network did not drop it due to congestion. No, it arrived, but it arrived in a later stage. And when I tried to play it out, I realized that it's too late for me to play it out at this point in time. So I decided to ignore it. Okay? And the idea here is that we can mitigate the network loss by using some reliable protocols, such as TCP. Okay? So we can mitigate the network loss using some reliability. So if the packet is dropped, I need to use some way of retransmission or recovering this packet somehow, whether using TCP, reliable transmission, or using error detection and correction from the data link layer, something like that. So we need to recover from this packet loss. But delay loss, so we learned one technique to mitigate this, which is the de-jitter buffer. Okay, so now we need to estimate what is the initial delay that we can wait for before we can play out the audio content, because based on this delay, I'll start playing out, and if the network jitter is more than this delay, then I will have a problem. Okay? So it turns out for typical live audio interactive chat, this delay is around 400 milliseconds. Okay? So this delay is the maximum typical delay difference between consecutive packets that is tolerable by the live audio chat application. Okay? So if the difference between one packet and the other is less than 400 milliseconds, I'm fine. Of course, I still have to use the buffer at the receiver in all cases. But if the jitter caused by the network is more than 500 milliseconds, then this will affect the quality of the conversation. Okay? So this loss tolerance depends on multiple factors. One of them is the type of encoding that you use. Okay? Is the type of encoding that you use for the audio. Because, of course, depending on the encoding, you can send less data or more data, less audio chunks or more audio chunks. And if it's less audio chunks, then the probability of having a large jitter will decrease. And based on that, this delay tolerance will change. Okay? So that depends on the encoding, and of course, it depends on the loss rate from the network point of view, or the delay from the network point of view. Okay? So it depends on two things. It depends on the encoding method or the encoding type, and it depends on the performance of the network type. So this is again the famous scenario, assuming that we have uncompressed audio, which means that the data is generated in using constant bitrate. So every fixed amount of time, you have another audio chunk of data. Of course, by the time it arrives to, so this is at the receiver. So at the receiver, it will arrive not necessarily in the same way, which means that some packets may have different delay, more or less than the other. So at any point in time, this is the jitter. This is the difference in the between two consecutive packets throughout the entire session. And the idea now is if I start playing at this point in time, which means I start playing here, so at this time this packet is there, and then when I try to do this, okay, so depending on of course, once I start playing, I should play in a constant rate, similar to when these packets have been generated, and in that case, I will have a problem here, for example, and so on. So some of these packets will be lost. So this delay now, or sorry, this wait time to play out the audio content is very critical, particularly in interactive applications. Okay? Because wait time does not affect the quality for the stored multimedia content, right? It does not affect the quality in any way, because it's not highly interactive. Okay? So you wait, and then you start playing out the multimedia content, but during live conversations, this delay would reflect on the quality that you start experiencing a delay in the conversation that the person is actually trying to give to you. So this affects the quality of the communication throughout the time. Okay? If you notice on Al Jazeera, sometimes the reporters will have this effect. So after some time of getting back and forth, you will start expecting that the person is disconnected or something, and Are you there? Or something like this. So that's what we're talking about. This affects the quality of the interactive conversation. This type of effect does not happen when you have a stored multimedia content, even if you are doing streaming, right? So interactive applications have this distinct characteristic. Okay. Right. So the receiver attempts to play out each chunk exactly q milliseconds after the chunk was generated. So this this q is the wait time that we are talking about. So if a packet was generated at time t, okay, the receiver will start playing this packet at a time which is t plus q. All right. So this q accounts for the network delay. Okay, it accounts for the network delay. So if that q increases, this means that, well, the packet will wait for some time in the buffer. Okay, will wait for some time in the buffer, which will affect the delay loss. So or the probability of delay loss. So if this q is high, okay, this means that the probability of delay loss will decrease, right? Because I will play the packet long time after it was generated, right? So it will have to stay in the buffer for a long time. Okay? So the probability of delay loss in that case decreases. So that's what we are concerned about now, especially for interactive applications. This parameter is really critical because on one hand, if this parameter is long, we said that the probability of delay loss will decrease, but what else could happen? The quality of the conversation will also decrease. Because if this delay or this wait time is long, this will account for the fact that you will start feeling long delays that the person is talking, and sometimes you see he's playing with his lips and stuff, but nothing is coming to you. So that's a problem. It affects the quality of the conversation. So it's a trade-off. If we reduce this queue wait time, then we increase the probability of delay loss. So we increase the interactivity, which means the quality of the conversation, but we also increase the probability of delay loss. Okay? Not the network loss, huh? We increase the probability of delay loss, not the network loss. Network loss depends on the performance of the network itself. Okay? Here we're talking about the delay loss. مفهوم الفرق؟ حد مش فاهم الفرق؟ Yeah, we're talking about the type of the loss. The loss we're talking about here is not the network loss. It's not the loss due to network congestion that the packet has been dropped. The packet has not been dropped. It arrived to the receiver. It went to the buffer. But it was too late. I should have played out this packet before it comes. So in which case, to me, it's useless. Okay? It arrived, but it's useless. So if for small queue, the interactivity is good, the quality of the conversation is good, but the probability of delay loss is increased. So that we can see from this figure here. So this is T. This is the time of. This is the time when the packet was generated. Okay. So if this is, of course T here is 0. So this is P. Okay. So in which case the play out time is T plus Q. Okay. So which means that I'm exactly here. I'm trying to play packet number 1 at this point. So packet number 1 has arrived, so I'm fine. So it waits for this time in the buffer. Okay? So I go to packet 2 has arrived. There's no problem. Packet 3 arrived, no problem. So packet 4, due to the fact that the jitter here is long, what happened here is that from this packet to this packet, the network was in a way highly loaded. So because this effect is dynamic, it changes over time, right? So the jitter in that case, for this instant of time, the jitter is high. It increased due to some network load, okay? So in that case, this packet arrived, but it arrived too late. It arrived here, where I should have played it here, okay? So to me, this is delay loss. It's not network loss, it's delay loss, okay? Okay? So this packet is lost. So the probability of delay loss here is 1 over the number of packets. For this particular scenario, the delay loss rate is 1 over the number of packets. Okay? The packet loss here is 0. Nothing has been lost. We're not, analyzing the effect of the network. We're analyzing the effect of delay loss. Okay? So if I decide to increase this time, so from P to P dash, so here P dash is long, okay? So in that case, I will start playing out here. So obviously, I have long wait time from when the packet arrives until I actually play. This wait time, okay, for multimedia stored content is not a problem. It's not a problem, right? You will click play. You will wait for a certain time, a few seconds, and then you'll start playing. You will not feel anything, and that's why typically for streaming multimedia, stored multimedia content applications, this time is allowed to be large enough, and that's why for some applications, when you click on play, you wait for 10 seconds, 20 seconds, and sometimes for a minute before you start seeing something. But once you start seeing the video has no pauses and it's continuous, which to you is tolerable, it's acceptable, okay? For interactive applications, it is not the case, okay? So this delay is really critical, and we need to customize it. And that's why we need to design this time carefully. So, of course, in that case, the delay loss is for this particular case, the delay loss is 0. Is 0. Delay loss is 0, and network loss is 0, right? Because none of these packets is not in the buffer. So this packet arrived and waited for this time duration in the buffer. This packet has arrived and waited for this time duration in the buffer. Okay? This packet has arrived here, and this packet has arrived here. Okay? So I'm playing the audio chunks way after they were generated. Okay? So for the person who is on the other side, he actually has to wait for this whole period of time, okay, before he can listen to the audio content. And sometimes this time duration is really long. And for live conversations, like for example that I just mentioned before, for reporters on international sites and stuff, you start feel there is long delay before you listen to anything coming from that person, and that gives you a really bad impression, okay? And in some cases, you feel like the person was disconnected, okay? So that's the low quality we're talking about now. All right, so the goal and what people are working on, or have actually studied that for years, is the concept of a adaptive playout delay. So for adaptive playout delay, the idea here is to minimize the playout delay. We want to minimize the playout delay, but not minimize it in the sense that we increase the delay loss, right? So we want to minimize the playout delay, but without increasing the delay loss. So what typically happens is that I start, so the conversation happens as follows. So this is the time horizon. So we start from 0. So we generate audio content like this. And then after some time, I stop, right? So I stop. I finished my sentence. So I'm waiting for the other person to respond back. After some time, I start generating other packets. And then I stop, right? That's typically how the interactive application works. After some time, I will start generating other packets and things like this. So what they try to do is that during these silence periods, they try to adapt the playout delay. Okay? So for some periods, I use possibly long or short. Well, my objective is to minimize it, but minimize it based on some network level measurements. So what happens is that during this period, so during this first sentence, or first بيسموها spurt of audio data, I start sensing the network. And I do some measurements to see what is the maximum delay from the network point of view. Okay? Based on these measurements, I will, calculate and estimate what is the best playout delay that I should use for this period. Okay? So here, initially, I can use a playout delay which is conservative, which is long. Maybe for this first case, I will start playing out, assuming that this is where they have to arrive at the receiver, and maybe I will take a conservative approach and start playing out here, which means that it's a conservative approach. So here the playout delay is a little bit large. But at the same time, while I'm playing, I'm actually doing some network measurements. And then here, maybe I can use a little bit more aggressive delay. So I will maybe select one which is here. Okay, based on some network measurements. Here, if the network delay is happens to be, increased, like for example, like this. Okay, so due to network congestion and network load and stuff, the jitters start to increase. Then, in that case, due to some measurements that I have done in this period, maybe I can go back and increase the playout delay to make it more conservative. So from one cycle to another, during the silence periods, what I'm trying to do is that I'm trying to estimate what is the best playout delay in the next period of time, based on some measurements from the previous cycle. So I'm dividing the audio content into cycles, and from one cycle to another, I'm trying to do some network measurements and adjust the playout delay in the next cycle. Okay? And I do that in a pipeline way. Okay? Any مفهوم ولا صعب شوية؟ Why am I seeing some weird faces يعني? Is it difficult ولا it's difficult? يعني to me it's easy, but maybe to you it's a little bit hard. I need some feedback just to assess whether it's hard or not. So this is how adaptive. طبعا again in stored multimedia content we didn't have to worry about this. ماشي؟ إنما it's particularly important for live interactive multimedia conversations. Okay. Okay. So that's the approach of adaptive play-out delay. All right. So similar to what we have done for the stored multimedia content, where we have studied the real-time streaming protocol, which is the application level protocol that's used to control the stored multimedia session, right? To set up the multimedia session and then facilitate the client interaction with the multimedia content, like pause and move forward or play from a particular location and so on, which is what we have talked about last time. For interactive applications where we have some live conversations, as you can imagine, the control protocol in that case is slightly different. And as a result, we have two possible protocols. One of them is what we call session initiation protocol. Okay, so session initiation protocol corresponds to RTSP, okay, but for interactive applications. You will find that it's highly similar to RTSP, but here you will find some small differences to facilitate the interaction during live conversation. Okay. So the long-term vision, of course, this long-term vision has been achieved now, or to a great extent it was achieved. Like this was a few years in the past where people were envisioning that all the multimedia conversations, all the live conversations will be done on the internet, which means that we don't need any phone lines. Okay, so we don't need any phone lines, or we don't need any dedicated network to facilitate these live conversations, like the most important one, which is ISDN. ISDN is a dedicated network for video conferencing. Okay, so in that case, it's actually circuit switched network. If you remember, in the beginning of the course, we talked about circuit switched networks, and we said that circuit switched network is deterministic in providing quality of service because we establish a virtual circuit which is dedicated. So in that case, it's easy to provide quality of service. But of course, the long-term vision, which has been achieved to a great extent nowadays, is to have the majority or even 100% of our voice conversations and video conversations over the internet, over the normal internet. But this requires, of course, the fact that the internet, having been a packet-switched network inherently, because the internet is packet-switched network, okay, it needs to have all the quality of service components which we have been talking about since the beginning of the course, including bandwidth management and admission control and scheduling and all these issues that we've been talking about. So assuming that we have all these components in place over the internet, now we are in a good position to just try to transition all the live conversations in terms of audio and video and things like that to use the internet, because the internet for us is almost free. So we can use it anywhere at any point in time using any device. So we can reduce the cost of international calls and conversations and conferencing and stuff using the live chat over the internet. So luckily we have this nowadays to a great extent. So that's the long-term vision. So we need to have all telephone calls over the internet. So we have WhatsApp, we have Skype, we have all these that we can use nowadays. People are identified not necessarily by phone numbers. We can identify people by emails. So on Skype, you just provide the email and you are identified. So you don't need any phone number or SIM card or something like this. So you can reach the person whom you're trying to call, no matter where they are roaming. Maybe they are traveling, they are in the car, here or there, and wherever you are, you have an IP. Okay, even if this IP changes, you don't care. Okay, using one identification for you, which in many cases the email, a simple email, you are identified, and you can conduct all your live calls and conversations and chats wherever you are. Okay, even if you are roaming from one network to another. Maybe now you are over Wi-Fi, now you switch to your car, now you are over 4G, and you move from 4G to your Wi-Fi at home. So during this whole trip, your call should be maintained, should be live and consistent all the way. Okay? So you can hand over from one network, you can move from one network to another, and you don't have to feel anything. So this vision is achieved, of course, by all the techniques that we have talked about so far. And because we are talking about live multimedia conversations where you can have a conversation between two parties, you need to have a control application layer, control protocol similar to RTSP, which in that case we call it session initiation protocol. Okay? So session initiation protocol gives you all these services, which we can talk about next time, inshallah. Okay? So that's what we need to talk about next time.